Perfect, thanks. Okay, yeah, so this is based on a joint work with Magee, Cheung, and Alfredo Nájera Chávez. And our goal is really to generalize the construction of projective toric varieties in terms of polytopes to the non-toric world. There's a lot of different levels of generality that you can work with here if you want to describe non-toric versions of this traditional toric construction. And I'll talk in a bit about where we would naturally aim to go, but for this work and for this talk, what we work on is the cluster world. So in a little bit, I'll tell you what a cluster variety is and why cluster varieties are interesting. But I want to start off by just reviewing the toric picture so we can essentially get a clear picture of what it is that we are trying to generalize. So a d-dimensional convex rational polytope defines a d-dimensional polarized projective toric variety. So starting with a polytope, we're going to get a projective toric variety.
COVID-19 pandemic has shown that this is unsustainable as a result of the requirement for social distancing of 2 meters.
Sorry, I've muted the participant. Please go ahead.
Okay. So yeah, starting with a polytope, we're going to get a projective toric variety together with some ample line bundle. And now the integral points of this polytope are going to correspond to sections of that line bundle L. And moreover, if we take dilations of the polytope P, this will correspond to sections of powers of the line bundle L. So let's just look at this in an example. And in this example, I want to highlight the importance of convexity for our polytopes. So if we just start with a triangle with vertices labeled X, Y, and Z, the first step of the procedure is to take the cone over our polytope. So if we go to, say, level R in this picture, the level R slice is just going to be R times the original polytope, the rth dilation. And multiplication of sections, or the integral points in the polytope picture, just corresponds to addition in this cone. So for example, if I have the vertex corresponding to point X and the vertex corresponding to point Z, well, if I add those vertices, I should get the vertex corresponding to XZ. So at level 2, I wind up with this polytope and corresponding vertices. At level 3, I get this polytope and corresponding vertices. At level R, I'll have, well, homogeneous monomials, degree R monomials in 3 variables, which is it's a basis for all homogeneous degree R polynomials in 3 variables. So in other words, what we're constructing is the line bundle O of 1 on P2. So this simple triangle gives us P2 together with the line bundle O of 1. And actually a little bit more, it gives us a basis for the section ring of O of 1 also. So next, a non-example to highlight the importance of convexity here. If I started with a non-convex polytope, well, the points X and Y here are in the polytope. They're integral points of the polytope. But when I take twice the polytope, the point XY isn't contained in twice the polytope. So in this picture, if we were to try to do the same construction, we wouldn't get a grading out. We wouldn't be able to get a graded ring. It wouldn't be something that corresponds to the section ring of some line bundle. So without convexity, we don't get graded rings. We can't take proj. The construction completely breaks down. So convexity is absolutely essential, and that's something that we'll want to generalize to the cluster world later on. So the picture that we really want to generalize now is this. So we're starting with a torus T, an algebraic torus, and M, the character lattice of our torus. And we want a cluster analog of this picture. M is a basis for the regular functions on T. Convexity in M tensor R determines which subsets of M are defined polarized projective compactifications x comma L of T. And the M points of S and its dilations give a basis for the section ring of L. So we'll want cluster analogs of everything in this picture. So the next thing to do is tell you what cluster varieties are. And well, just giving the definition of a cluster variety is a little bit unsatisfying and sort of unmotivated. So they really fit into a broader geometric picture known as log-Calabi-Yau geometry. So a log-Calabi-Yau variety is a smooth complex variety U with a unique volume form omega having at worst a simple pole along any divisor in any compactification of U. So we have some variety U and it's not compact, or at least not necessarily compact. And with such a variety, there could be many ways that we could embed it in some compact space, or we could compactify U. But in this definition of log-Calabi-Yau, the sort of key thing, the key feature is that no matter how we compactify U, this volume form omega will have at worst a simple pole along any boundary, any divisorial component of the boundary that we've added. And the simplest example of one of these is just the algebraic torus. So in this case, the log volume form is, well, the volume form is the usual log volume form, dz1 over z1, wedge dz2 over z2, and so forth. And if you think of your favorite toric variety, it's not so hard to prove that this volume form has exactly a simple pole along all torus invariant divisors, or supports of torus invariant divisors. And maybe the easiest example is just going into, well, to partially compactify the torus to get to c to the n, partially compactifying c star to the n. So if you think about the coordinate hyperplanes, well, this clearly has a simple pole along the locus z1 equals 0. And all other, well, z1 equals 0 to zn equals 0 are pretty easy to see. Any other possible toric divisor, you'll have to do some change of basis, but it's also not so difficult to see that, or change of coordinates, but it's not so difficult to see that omega will have exactly a simple pole along all of your torus invariant divisors. The next example is essentially many copies of the first example. So we could take a bunch of tori and glue them together in some careful way using birational maps, where what we'll require is that the canonical volume forms on each torus patch together to give us a global volume form. So the pullback of omega on the torus Tj will give us omega I, the volume form on Ti. And this sort of very simple example is what we call a cluster variety. So people who know about cluster varieties might object that there's more things that are asked for something to be called a cluster variety, but okay, this is morally what I want to think of as a cluster variety here. Okay, so why would we look at toric varieties? It seems like it's a very, at cluster varieties, it seems like it's a very simple construction. And there's no reason to really hope that this will be something important in mathematics, but it turns out that it is. Well, the first reason to look at them is just that they are simple. They're almost toric. So there's some hope that constructions from toric geometry could generalize to this cluster setting, where instead of having just a single torus that we're embedding into our variety, we have a union of a bunch of tori glued together through birational maps. It's similar to the toric geometry picture. So there's some hope that we might be able to generalize from the toric world to the cluster world. Next, it's a lot simpler than the general Log-Calabi-Yau setting. So it's more general than toric varieties, but less general than Log-Calabi-Yaus, where things can be a bit tricky to work with. So really the setting that we would want to work in here is something called affine Log-Calabi-Yaus with maximal boundary. But the machinery to work in this level of generality isn't fully developed yet. So we sort of work with what's available. And even though this is a somewhat simple setting, it's still something that's interesting in a lot of different areas of math. So cluster varieties show up in representation theory, integrable systems, hyperbolic geometry, quantum groups, even in computations of scattering amplitudes in physics. And I know they're also a big deal in the Fano search program. So this is something that's sufficiently simple to actually do some proofs and calculations, but also sufficiently general that it's something that really is interesting in math in a lot of different areas. Okay, so what are we going to use to study these then? So the main tools are some combinatorial gadgets called scattering diagrams and broken lines. And these are really tools from the Gross-Siebert mirror symmetry program. So I won't really have enough time to say precisely what they are, but I want to sort of give you a rough idea of what scattering diagrams and broken lines are. So roughly, a scattering diagram is a collection of walls in a piecewise linear manifold, U trop R. So these, well, first U trop R. In the toric case, you can just think of the co-character lattice tensor R. This is some piecewise linear manifold that encodes the logarithmic geometry of U. So if you think in the toric case, the co-character lattice of a torus is what tells you about divisors on your torus that you can add to your torus to get toric varieties. You usually draw a fan in N tensor R, and the rays of your fan correspond to divisors. Each ray has some primitive generator, some co-character, and the those co-characters then are giving you toric divisors. So U trop R is going to play the same role in the Log-Calabi-Yau case, and in particular in the cluster case. Walls are codimension 1 rational convex cones living in U trop R that come decorated with a function, the scattering function. So these things are used to construct a canonical algebra. So this algebra is determined by the logarithmic geometry of U, and at least conjecturally, in the affine Log-Calabi-Yau with maximal boundary case, the algebra that's constructed is conjectured to be the algebra of functions on the mirror. So this actually, since, again, restricting to the affine Log-Calabi-Yau with maximal boundary case, since we're in that affine setting, this actually gives a construction of the mirror, at least conjecturally. You build an algebra, you just take spec of that algebra. And yeah, this is a major thing in the Gross-Siebert program, constructing mirrors to affine Log-Calabi-Yaus with maximal boundary. So an example of this, if we start with Y being the Del Pezzo surface of degree 5, and D an anti-canonical cycle of 5 lines in Y, so some pentagon, Y minus D is a cluster variety U, and the scattering diagram for it is the one pictured here. Okay, so we have, in this case, 3 walls. 2 of them are just the axes, and the last one is a ray. Now, if you want to imagine something like the toric case, each one-dimensional cone in this picture corresponds to one of the 5 components of our anti-canonical 5 lines. Okay. So next, broken lines are what we'll use to construct this canonical algebra. So the algebra will come equipped with a basis. We'll define the algebra in terms of the basis and some multiplication rule. But these basis elements in terms of broken lines. So roughly speaking, a broken line is a ray in U trop R that's allowed to bend in some prescribed fashion at walls. So I mentioned that U trop R is a piecewise linear manifold. So it wouldn't even make sense to talk about just a ray in the usual sense. We don't have a notion of linearity, but we do have domains of linearity in U trop R. And if we look between walls, well, regions between walls do have a linear structure. So we'll ask that wherever this ray can be linear, that it actually is linear. And when we cross a wall, there's going to be some prescribed fashion in which it's allowed to bend. Next, each linear segment is going to be decorated with a monomial. This monomial will correspond to the negative of the velocity of our ray. So the ray's some path, the negative of the velocity there will give us the exponent vector for our monomial. And the monomial together with a scattering function will determine how our rays are allowed to bend. So here's an example. If we start off in the -1, 0 direction here and come in and hit this wall, this monomial, z to the -1, 0, and this scattering function, z to the 0, 1, determine how this ray is allowed to bend. It can either go straight or bend down this way. Now, it's usually a slightly more complicated than this, but if you just multiply z to the -1, 0 by 1 plus z to the 0, 1, well, these two terms are the monomial summons of the result. So we have z to the 1, 0 times 1 is, z to the -1, 0 times 1 is z to the -1, 0. Z to the -1, 0 times z to the 0, 1 is z to the -1, 1. Generally, there will be some exponent. We would have 1 plus z to the 0, 1 to some power here. But in this example, that power is 1. But yeah, essentially, the allowed bendings just come from an expansion of some product, and monomial summons give us decorating monomials for the bendings. So how do we use these to get a basis of regular functions on the mirror? So we'll get one theta function for each tropical point, each integral tropical point, P and U trop Z. So this is like saying that the co-character lattice of a torus is a basis for regular functions on the dual torus. Here we'll have integral tropical points of U corresponding to divisors we can add to U being a basis for regular functions on the mirror U check. So we can write these down in local coordinates. The choice of local coordinates corresponds to choosing a base point in our piecewise linear manifold U trop R. So we'll pick some base point Q, and then the theta function theta p in this local system of coordinates will be written as a sum of decorating monomials of broken lines that start from the direction P and end at Q. So if we want to write the theta function theta minus 1, 0, we start in the direction minus 1, 0 here. So our initial exponent vector is minus 1, 0. Our initial decorating monomial is z to the minus 1, 0. And now we look at all the broken lines that start with that initial decorating monomial and end at the base point Q. Well, there's only 2 of them, and there are these ones shown here. And now we'll just add the decorating monomials in the final domains of linearity. So what this picture is showing is that theta minus 1, 0 in the system of coordinates corresponding to this base point Q is z to the minus 1, 1 plus z to the minus 1, 0. These broken lines really come from tropicalizing holomorphic disks in, or at least conjecturally, they're heuristically supposed to correspond to tropicalizations of holomorphic disks, so-called Maslov index 2 disks, and bends at walls, at least heuristically, should correspond to gluing in Maslov index 0 disks. So if you have a Maslov index 2 disk and a Maslov index 0 disk that you've glued together, well, the Maslov index 0 disk doesn't change Maslov index, so you start off, you wind up with another Maslov index 2 disk. So that's just some rough stuff from symplectic geometry that serves as a heuristic for the whole Gross-Siebert program in terms of scattering diagrams and broken lines. But there is some symplectic heuristic that goes on behind the scenes to construct these pictures and theta functions. So I've told you that these theta functions are supposed to correspond to a basis for regular functions on the mirror. Well, we can multiply regular functions. Regular functions form a ring. So there had better be some way to take a product of 2 theta functions and decompose that product as a linear combination of theta functions. So the thing that we're constructing had better be actually an algebra, not just a vector space. Well, there's a nice result of Gross-Hacking-Kiob-Kontsevich that tells us exactly how to compute the structure constants alpha, p, q, r. And it's a very combinatorial rule. It looks a bit ugly at first, but it's not so bad after you parse it. What this is saying is that the structure constant alpha, p, q, r is given as a sum where the thing that what we're summing over is pairs of broken lines, gamma 1 and gamma 2. And these pairs of broken lines are required to satisfy certain conditions. So first, gamma 1 is going to correspond to P, gamma 2 is going to correspond to Q, and the correspondence is this way. So the initial exponent vector for the decorating monomial of, so So gamma 1 will have some unbounded domain of linearity corresponding to the direction it comes in from infinity. And that unbounded domain of linearity has some attached decorating monomial. The exponent vector of that decorating monomial, we require to be p. Similarly, for gamma 2, the corresponding exponent vector for that unbounded domain of linearity will be q. Then the endpoints for both gamma 1 and gamma 2 will be r. And then the final exponent vectors, so the exponent vectors right near that base point r, are required to sum to r. So this is some form of tropical balancing condition. This balancing condition in geometry world instead of tropical world, well, this really corresponds to building up a tropicalized projective line, some tropicalized P1. So this will correspond to some embedding of P1 with certain tangency conditions at infinity. These things that appear inside of the sum are really just encoding multiplicities. So if we were to have some more complicated bending, in principle, the decorating monomials can pick up coefficients. For example, if we had an exponent, if instead of having the exponent of this scattering monomial being 1, if we wound up with an exponent of 2, then, well, one of the binomial coefficients would be 2. So we would have, we could have an additional broken line where the term for our intermediate broken line here would have a coefficient of 2 instead of 1. So these C's are encoding multiplicities in that sense, where our decorating monomials can pick up some coefficient. And we're just taking a product of those multiplicities, and alpha PQR is given in that way. So let's just see how this works in an example. So if I want to multiply theta -1, 0 and theta 2, 1, well, first I'm supposed to look at broken lines whose initial decorating monomial is e to the -1, 0 on this side. So both of these satisfy that. For theta 2, 1, I want my initial decorating monomial to be z to the 2, 1. Both of these satisfy that. And then I want to end at a base point such that my exponent vectors sum to the coordinates of this base point. So -1, 0 plus 2, 1 is 1, 1. And -1, 1 plus 2, 1 is 1, 2. So you could look for other examples. It turns out these are the only two pairs of broken lines that satisfy these conditions here. And as a result, we can write down this product as theta -1, 0 times theta 2, 1 is theta 1, 1 plus theta 1, 2. Okay. So it's just some explicit combination for writing down our structure constants, and we can see how we can recover the product from it here. Okay, so where are we so far? What we want is a cluster analog of this picture, where the character lattice of a torus is a basis for its regular functions. Convexity in the character lattice tensor R determines which subsets of MR define polarized projective compactifications, X comma L of the torus. And the actual lattice points in MR of the lattice points in S of, and its dilations give us a section ring of this line bundle L. So that's what we're trying to build a cluster analog of. And so far, instead of M, we're going to have U trop Z. So U trop Z, the integral tropical points of U, will give us a basis, the theta basis, for regular functions on the mirror U check. So from here, what we want is ideally some convexity notion in U trop R that will let us identify when a subset of U trop R defines some polarized projective compactification, in this case of U check, of the mirror U check. And ideally, those tropical points, integral tropical points of these subsets and dilations of these subsets should give us, again, a theta basis for the section ring of our line bundle. So the question we're at now then is there some convexity notion that says when S, a subset of U trop R, defines some compactification of the mirror U check? Said in a more algebraic way, when do S and its dilations define a graded ring? Okay, so that's the question we want to address. And the first thing I want to do is make it more precise. So Gross, Heckenkill, and Kontsevich defined something that they called a positive subset. So if we have a closed subset of U trop R, this is said to be positive if for every pair of non-negative integers A and B, every P an integer point in A times S, Q an integer point in B times S, and R some element of U trop R, some integral element of U trop R with alpha PQR non-zero, we have R is an element of A plus B times S. Okay, so that's sort of a mouthful, but after you break it down, it's very natural. All we're trying to do is get a graded ring out. So if I have something in level A times something in level B, the result had better live in A plus B. So if I'm going to get a graded ring out, I need my eighth homogeneous piece times my bth homogeneous piece to lie inside of my A plus bth homogeneous piece. And positive is just explicitly laying out that condition. All I'm asking for is that dilations of my subset respect theta function multiplication so that we can get a graded ring out. Okay, so the new question then is, when is a subset S of U trop R positive? Okay, so maybe I should stop for a second. Are there any questions up to this point? Or is everything okay?
At least there is no question in the chat. So I guess everything is fine so far.
Okay, great. Thanks. Oops. Great. So with that in mind, we make a definition. So the natural way to generalize convexity from a linear manifold to this tropical space, this piecewise linear manifold, well, essentially we're going to replace lines with broken lines. So we say that a closed subset S of U trop R is broken line convex if for every pair of rational points X and Y, every broken line segment connecting that pair of rational points X and Y is entirely contained in S. So in a usual real vector space, there would only be one line segment connecting 2 points X and Y, and S would be convex if and only if, for all pairs of points, that line segment connecting X and Y was contained in S. But in this piecewise linear world, there could be many broken line segments connecting S and Y, X and Y. And what we're going to ask is that every such broken line segment connecting X and Y is entirely contained in S. So it's just the natural notion, the natural generalization of convexity to this real tropical space. Okay, and our main theorem is that this notion of broken line convexity does exactly what you would hope. It gives exactly the thing for cluster varieties that usual convexity does for toric varieties. So S if and only if S is broken line convex. So broken line convex subsets of U trop R are exactly those subsets that define compactifications of the mirror you check through some proj construction. So this is what we had wanted to generalize. And this is what we have now. We have exactly that generalization. Broken line convexity in U trop R determines which S in U trop define polarized projective compactifications X comma L of U check. And the U trop Z points of S and its dilations give a basis for the section ring of L. Okay, so next I want to give an example and then a non-example of broken line convex and therefore positive polytopes or subsets. So this polytope here, well, there's no way that I can have a broken line that has, say, endpoints in this blue region, but is not entirely contained in the blue region. Essentially, what's going on is that every bend here, every bend toward the origin, is actually greater than the maximal bending that we could have for a broken line segment. This polytope gives actually the anti-canonical polytope for the Del Pezzo surface of degree 5. So I had mentioned that this scattering diagram gave us the scattering diagram gave us the space U, which was the complement of the anti-canonical divisor in the Del Pezzo surface. Well, we can take that space U and compactify it again to get our Del Pezzo surface using this polytope. So we would do the same thing as in the toric world. We take the cone over this picture, and now we have relations between generators of our ring that are more complicated than in the toric world. The cluster relations come from those structure constants that we were looking at earlier, but it's still essentially the same idea. We build some braided ring from this polytope. It comes equipped naturally with some bases, and well, you can work out that the ring that you get is precisely the anti-canonical section ring of the Del Pezzo surface of degree 5. And that was originally worked out in an example of Grosek and Kiełkoncewicz as well. So this is a non-example now. So this square might look convex, but it's not broken line convex because we could have for example, endpoints at these two corners, this red line segment, broken line segment, isn't contained in this square. So while this square is convex, it's not broken line convex, and it doesn't define for us some compactification of our mirror U check. Okay, so unless there's any questions from here, I want to get into some applications. Okay, yeah, so the first application is that we can have essentially an intrinsic version of a Newton-Okounkov body, at least in the cluster context. So just a little reminder, if we have X a d-dimensional variety and D a divisor on X, let R sub D be the section ring of D. So R sub D is going to be a graded ring where the homogeneous component of level J, the jth homogeneous component, corresponds to the sections of O of X twisted by J times D. So we're allowing poles of order J along the divisor D that we've added. So if we have now a valuation from the section ring of D minus 0 to Z to the D, a lattice Z to the D, the usual Newton-Okounkov body is defined in this way. So we take the images of all of these homogeneous pieces under our valuation, and then we rescale them by 1 over J. We take the union over all J from 1 to infinity, take the convex hull of all that, and then take its closure. So these are supposed to be a sort of a non-toric version of a Newton polytope. And they show up a lot, for example, studying toric degenerations. But in Newton-Okounkov world, there's lots of different choices of valuations that you can make that will give you different Newton-Okounkov bodies. And generally, there's not really some God-given valuation. But it happens that in the cluster world, you really do have something God-given. So to get an intrinsic Newton-Okounkov body for a cluster variety, we'll take X to be some partial minimal model, some partial compactification of U check. This is just a partial compactification where any boundary, so if we've added some divisors, each divisor that we've added to get X from U check is such that our volume form on U check has a pole along that component. So in the definition of log Calabi-Yau, we required that in any compactification, omega would have at worst a simple pole along the divisors that we add. For a partial minimal model, you'll require that any divisor that you add, this volume form does indeed have a pole. So we're going to be looking at those sorts of compactifications. So now let D be a divisor on X and RD the section ring of D as before. Well, we can give something that's analogous to a Newton polytope in the toric world, but we'll use theta functions instead of characters. So an arbitrary regular function, we can write as a sum of theta functions. And we'll define the theta function analog of the Newton polytope of this regular function to be now the broken line convex hull of all those tropical points P such that A sub P is non-zero. So any theta function that actually contributes here to this sum will take the broken line convex hull of those corresponding tropical points. Now, broken line convex hull means exactly what you would expect. It's just going to be the smallest broken line convex set that contains all of these P. So using that, we'll define an intrinsic Newton-Okounkov body in this way. So now we're looking at all F in the jth homogeneous component. And we'll take the theta function analog of the Newton polytope of all of those guys, rescale by 1 over j again. And then again, we're taking this union from j equals 1 to infinity. We're replacing the usual convex hull with a broken line convex hull, and again, taking a closure. So this is some natural analog of a Newton-Okounkov body that will live in a tropical space instead of a vector space. And well, a choice of torus in our chart will give us an identification of this intrinsic Newton-Okounkov body with a Newton-Okounkov body in the usual sense. Essentially, there's every choice of torus will correspond to a valuation, and it will identify tropical points with vectors in some lattice. Okay, this is some definition that can be made, but I need to convince you that this is actually a good definition to make. Well, together with Lara Bolsinger, we looked at this for Grassmannian's Gur Kn, arbitrary Kn. Connie Reach and Lauren Williams study Newton-Okounkov bodies for Grassmannians using a certain valuation associated to combinatorial objects called Plavit graphs. And so if D here is the pullback of a hyperplane class under the Plücker embedding, then they show that for certain Plavit graphs, which will correspond to certain torus charts in the atlas of our cluster variety, the corresponding Newton-Okounkov body has a very simple description. It's just the convex hull of the valuations of those Plücker coordinates, of all Plücker coordinates. So yeah, obviously the Plücker coordinates generate the homogeneous coordinate ring of the Grassmannian, and Lauren and Connie show that using these valuations coming from Plavit graphs, in certain for certain nice choices of Plavit graphs, the Newton-Okounkov body, which generally is this closure of an infinite union of things, it has this simple description as just a convex hull of things that already show up at level 1, namely valuations of the Plücker coordinates. But this description fails for other Plavit graphs or other toric charts. Well, all of these Plücker coordinates are in fact theta functions, and let's just write the Plücker coordinate pj as theta sub nu j. And then if we write things this way, then this intrinsic Newton-Okounkov body will always just be the broken line convex hull of all of these nu j's. This construction doesn't make any reference to a choice of torus at all. So it's independent of torus chart or independent of Plavit graph. So it's something where this very simple description holds in general in this intrinsic setting. And a completely analogous result holds if you replace Grassmannians with flag varieties. So this definition might look a little bit more complicated in that we're using machinery like scattering diagrams and broken lines. In practice, at least in these two examples, it seems that you get something that's very simple, simpler than the usual Newton-Okounkov construction. And I think it's not so much to expect that this should usually be the case, because in this context, you're dealing with really intrinsic objects. You're avoiding making choices. And I think in general, at least in mathematics, if you can avoid making choices, it's a good idea to do that. So the final application is to, well, hopefully give a version of Batyrev duality for varieties instead of for toric varieties. So this is really based on various joint works, and some of them are done, some of them are in progress, and some of them are just kind of nebulously planned at this point. But these are joint works with the following people, or subsets of the following people: Lara Bossinger, Mandy Cheung, Bosco Frias Medina, and Alfredo Nájera Chávez. So I want to start off with some basic definitions here to set the stage for what we're looking at. First, a Gorenstein-Fano variety. So a normal variety X is Gorenstein-Fano if its anti-canonical divisor is Cartier. So this part corresponds to the Gorenstein condition, and ample. This corresponds to the Fano condition. So we'll be looking at Gorenstein-Fano varieties here. Next, a lattice polytope P in M sub R is reflexive if its dual, just under the natural vector space pairing or lattice pairing between M and N, is also a lattice polytope. So of a reflexive polytope plays an important role in Batyrev's Batyrev duality for toric phanos. So the connection is that if X is a d-dimensional Gorenstein-Fano toric variety, then its anti-canonical polytope is a d-dimensional reflexive polytope. Moreover, if P is a d-dimensional reflexive polytope, then the projective toric variety associated to P is Gorenstein-Fano. Now, if X is some Gorenstein-Fano toric variety and D is some anti-canonical divisor, then by the adjunction formula, the canonical divisor of D is trivial. Kx plus minus Kx is 0. And the Gorenstein property implies that at least generic D will have at worst canonical singularities. And what this implies is that if we combine these two things, canonical divisor being trivial and D having at worst canonical singularities, the anti-canonical linear system of X consists of mildly singular Calabi-Yau hypersurfaces. So Calabi-Yau hypersurfaces with at worst canonical singularities. So now we get a Landau-Ginzburg mirror so if D is just a sum of these divisors corresponding to co-characters Ni, if that's the anti-canonical divisor of X, the toric anti-canonical divisor, then the Landau-Ginzburg potential is just a sum of the corresponding co-characters on the dual torus, or characters on the dual torus, co-characters on the original torus. And then for the Batyrev dual, the level sets of W are almost Calabi-Yau, but they're not compact. And we can fix this by trying to view W as a section of some OY of D prime where Y is a compactification of the dual torus, some toric variety compactifying the dual torus. D prime will be a divisor on Y. So the sort of minimalistic approach here, this least thing that we can do if we want to view Y as a section of some O of Y twisted by D prime is to just take the toric variety associated to the Newton polytope of W. So the Newton polytope of W will give us some reflexive polytope. In fact, it's the dual to the original anti-canonical polytope for X comma D. So as a result, Y is also a Gornstein-Fano toric variety. And in this picture, W and the other sections of OY of D prime are mildly singular calabi-Als. And okay, this result or conjecture, depending on which version of mirror symmetry you want to use, is that the sections of OX of D and OY of D prime are mirror calabi-Als. So this is what we want to generalize to the cluster world. And it works essentially, or we hope it works exactly the same way. So now we'll have a Fano minimal model of a cluster variety U. D will be a sum of components now corresponding to tropical points of U instead of co-characters of T. The Landau-Ginzburg potential is the sum of the corresponding theta functions on the mirror. And the integral points of dilations of our, well, okay, so we can define our anti-canonical polytope by putting R equal to 1 here. But dilations of this give us a basis, a theta basis for OX of R times D. We'll essentially replace the vector space pairing, or the pairing between lattices, with something called a tropical pairing. So kind of by definition, the points of U trop Z are divisorial discrete valuations. These are just discrete valuations on the field of rational functions of U, given by order of vanishing along some divisor. And, well, we've said that points of U check trop Z will parameterize, well, I've said it in the mirror way, but points of U check trop Z will parameterize theta functions on U. So we can just restrict the evaluation pairing then to get a pairing between U trop Z and U check trop Z. So some integral tropical point of U trop Z and an integral tropical point of U check trop Z. Well, I'm going to interpret this P as giving me a theta function, and this nu I'll keep as being the divisorial discrete valuation, and I'll just apply nu to this theta P. We could, of course, go the other way, and at least conjecturally, that's symmetric. And it's known in some examples or under certain conditions. So I want to get a notion of a dual polytope and relate it to the potential. Well, I can just take the theta function analog of the Newton polytope of W as the broken line convex hull of the integral tropical points is associated to summons of W. And I can define a dual in terms of the tropical pairing. And theorem, well, at least up to rational points, the dual of Newt theta of W is the same as our original anti-canonical polytope. And our proposed Batyrev dual in the cluster case then is exactly what you would expect. We know that Newt theta of W defines a minimal model Y comma D prime of our mirror. And our guess is that generic sections of OX of D and OY of D prime or mirror mildly singular Calabi-Yau varieties. So this is something that we don't know yet, but that we hope and we're actively looking at. That's all I have time for. So yeah, thank you.